Okay, so people will keep joining now. It's 6 o'clock, so I'll start with the presentation. So, hello all, I am Somnath Hazra, and this is a week 1 introductory session on operating system fundamentals, CS100 NOC 2022, and this is an NPTEL live session. I am a PMRF student, PhD student at IIT Kharagpur, and we'll be holding these kinds of sessions every Tuesday at the same time. So we will be discussing that some problems related to that week's lectures in the CS100 course, and these discussions will help you to solve the assignment questions. So just give me 1 second, I'll just see if the other people can join. Yeah, so I guess everybody is able to join. Okay, so I'll resume. Okay, so let's have a look at some problem questions. So this is the first question. So which among the following can you think of as a can run a user generated instruction? Which among the following systems can you can run a user generated instruction? What do you think? That is single user systems, multi-user systems, handheld computers, or embedded systems. So which according to you is the correct answer? There can be multiple answers also. So if anybody wants to contribute. Okay, let's go to the answer then. So except for embedded computers, all the others can actually run a user generated instruction. So by user generated instruction, we mean to say that even the embedded computers can run some instructions, right, that can be generated by the user, but they are not as per se generated by the user. For example, the embedded computers that you find in an ATM machine or a washing machine or so on and so forth, they have some limited set of instructions and user can select among them. But in other systems like the single user systems or multi-user systems or the handheld computers, an example of handheld computers of course is a smartphone. Nowadays the smartphones can use the smartphone to compile or run some user generated instruction. Of course you cannot they have very low processing power compared to the single user systems or the multi-user systems, but of course but they can process instructions, and that is what is asked in the question. Single user systems, as we know, can access the personal computers that we have in our homes. Multi-user systems, a very good example of a multi-user system is the server, which can give access to multiple users at the same time. That is, multiple users can work at the same time. But with the advancement of processor technologies and the chip technologies, nowadays the processors, even though they are single user processors, but they can be installed in servers also. I have seen i9 processors being used in both single user systems and multi-user systems, and they are working flawlessly. So that's not a problem. Of course, on multiple scale that might be a problem, but yeah, for a miniature scale, of course, it works flawlessly. So anyway, these three can run a user generated instructions, but embedded computers cannot. So now moving on to the second question, what is an objective of an operating system? Is it to make the hardware usage more efficient? Is it to make the system easier to use? Is it to make it easier to solve user problems, or all of the above? So if anybody wants to contribute. Okay, let's go to the answer. So it is actually all of the above. So any of the options are correct actually, but the best option will be all of the above. So operating system, as we know, it provides the bridge, it provides the gap between the hardware and the user that wants to use the hardware. So of course it makes the system easier to use, and user problems yes, the hardware that is present, it is required to solve user problems, but we do not actually know how to interact directly with the hardware, and operating system provides us a medium to interact with that hardware. So yeah, so it is all of the above, so all of the above are true. So now let's go to the next question. So which part of the system runs at all times when it is working, that is when it is switched on? Can anybody tell? Is it the system software, is it the application software, is it the kernel, or is it none of the above? Okay, let's go to the answer. So the kernel is the part of the system that runs at all times when after it is switched on till it is switched off. So neither the system softwares nor the application softwares, it's the kernel that is working at all times, and it is actually the most important part of the OS that is always kept in the RAM, so that the computer keeps on working. So it's just the required part of the OS that is kept on RAM. So let's move on to the next question. So can anybody tell me where the bootstrap program is stored in? So this is a very easy question. And this is a pretty simple question. Like, where is the bootstrap program stored in? Is it the random access memory? Is it the read-only memory? Is it the secondary storage disk? Or is it none of the above? Okay, in the meantime, I'll just check once again if the people are able to log in. Okay, I guess people can join. Yes. Okay, I see that you are answering in the chat box. Okay, for me to access the chat, I need to connect through another device. Since I cannot access the chat, just give me some time. I will just connect. So I'll just send a test message and check. Okay, now I can access your chat messages. So sorry for the miscommunication. I could not actually see. Sorry. So let me go back to the presentation. So yeah, can anybody answer this again, please? Where do you think is the bootstrap program stored in? Yes, Dhruv, it is correct. It is stored in the read-only memory. That is, the bootstrap program, as we all know, is the first program that is loaded for the system to be working, and it is kept. Read-only memory is actually a part of the random access memory, and that it is where the It is where the bootstrap program is stored. And actually it is said that nothing should be changed in the bootstrap program, otherwise it can mess up the operating system and it can mess up how the operating system works. So that is why it is an important part that is stored only in the read-only memory, and it cannot be changed and it cannot be accessed randomly like the other parts of the RAM. So it is only read-only. It is stored in the read-only memory. And secondary storage disk, it does not make sense, because if the bootstrap program if you store it in the secondary storage disk, it cannot be accessed as fast as required by the processor to start up the operating system at the start. So yeah, it is the read-only memory. Yeah. So moving on to the next question. So what happens during an interrupt? The control is transferred to the interrupt service routine. The interrupt architecture saves the address of the interrupted instruction. The OS preserves the state of the CPU, or all of the above. Can anyone contribute to this answer? Okay. Anybody else? Okay, yes, all of the above is correct actually. So yeah, all of the above is correct. That is the what happens during an interrupt is that it wants what generally happens is that it wants some kind of hardware access or something. So it needs to save up till which instruction it has executed, and then the next so the next instruction, so the address of the next instruction needs to be saved, and the OS preserves the state of the CPU. That is, the state of the CPU does not necessarily mean that fetch, execute. Sorry, is anybody asking some question? Hello. Okay, so the OS needs to preserve the state of the CPU means that it needs to preserve the register states, the program counter state, etc. The program counter, of course, is also another kind of register. So yeah, it needs to preserve the states of the CPU so that it can reload with that state when the interrupt is finally over, and the interrupt service routine is finally done with the execution. And of course, the OS has nothing to do with the interrupt, so it the core of the OS transfers it to the interrupt service routine, which actually attends to the interrupt. So yes, all of the above is correct. So let's move on to the next question then. So yeah, one routine of the interrupt service routine can handle. Can you provide the best answer according to you? That is, how many routines, how many interrupts can one ISR handle? That is, one interrupt, a few interrupts, any number of interrupts, or it cannot handle any interrupts? Can anybody answer? Okay. Okay. Anybody else? People are still joining. If anybody is dropping off due to some problem from my end, please tell me, okay, or just write a text or something so that I can look into it, because I can see people dropping off quite frequently. Okay. Anyway, so yeah, one interrupt is actually correct. So yeah, this is a pretty straightforward question. So let's move on to the next question. So on facing an interrupt, the transfer of the control to the ISR is made through system processes, bootstrap program, interrupt vector, or interrupt kernel. Which of among the following do you think is the correct answer? Okay, anyone else? Bootstrap program. Okay, anyone else? Interrupt vector. Okay, anyone else? So I'll tell you what system processes are. System processes are actually the system. Yeah, there's nothing much to explain about the system processes. So yeah, it basically they are. There are two types of programs actually. One are the application programs, the other are the system programs. So yeah, the application programs are basically the written in high level languages such as C, C++, C Sharp, or Python, etc. So they are actually the application programs that you install in a computer. For example, Microsoft Word is an application program, or the browser that I'm using, Google Chrome, that is an application program. So these are examples of application programs. But on the other hand, system programs are written in low level languages, and they actually interact more with the operating system and the core of the kernel rather than the application programs. And yeah, but the system processes are not really involved with the ISR. ISR is a special part of the operating system itself. So those are not the things. So bootstrap program, as I said in the previous slide, bootstrap program has a different functionality. It is required for the starting of the computer itself and the system itself. So that is not. So yeah, sorry. So that is not the work. Providing an interrupt service routine is not the work of the bootstrap program. So it does not solve that problem. So bootstrap program is not the answer. Interrupt vector, yes, that is ISR. Yes, it uses the interrupt vector to serve the interrupt. And interrupt kernel, I do not know whether it is a valid term or not, but I have to. I don't think it is a valid term. So yeah, I basically it's nothing. So yeah, interrupt vector is the answer. So yeah, let's move on to the next question. So now we come to the memory storage hierarchy. I hope you all have gone through those lectures also. So which among the following memory storage is mostly volatile in nature? Main memory, secondary memory, tertiary memory, or none of the above? So can anyone answer? Okay. Ornab says main memory. Raj says main memory. Anyone else? Okay. Okay. So everybody is saying main memory. Yeah. So main memory is the correct answer. Main memory, as we know, random access memory is generally referred to as the main memory. So secondary memory and tertiary memory, of course, they are not volatile. They are the memories that mostly hold the most of the data when the computer is switched off. So yes, main memory is the answer, and it is actually faster, kept higher above in the storage hierarchy, as you may know. As you go down the storage hierarchy, the storage structure, the storage devices become less volatile, and above this as you go up the storage hierarchy, it becomes more and more volatile. For example, the registers, the caches, or the main memory, they are all volatile in nature, but the secondary storage, the tertiary storage, they are all optical disks, for example. They are non-volatile in nature in general. So yeah, so main memory is the answer. So now we move on to the next question. So which among the following storage is the fastest according to you? Can anyone answer? Optical disks, magnetic tapes, registers, or do you think all are equally fast? Okay, okay, okay. Anyone else? So yeah, registers are the fastest. So the memory storage hierarchy is created in that way. So two things are kept in mind while creating the memory storage hierarchy. That is cost per unit bit and the speed of access of the device. So yeah, registers are kept highest. So they are the fastest among all the storage devices, and but they are also the costliest. So they do not have much storage space. So they are kept. There are very less number of registers that can only store very specific things. In fact, some of the registers have very specific duties and cannot hold any general data. For example, the program counter, as I said previously, it can hold only the address of the next instruction that that the operating system is going to execute. Only that much is held in the program counter. So yes, some of the registers have very specific jobs and cannot store any general purpose data. So below that come and of course the registers are tightly coupled with the CPU itself. They are on chip storage devices. That is, since then you need the CPU needs to access registers very fast. So they are kept on the chip so that they do not have that bus latency. They are not connected by wires and so on. So that the data is accessed within seconds. So not even seconds, faster than that, way faster than that. So the data can be accessed directly. Beyond that, there comes the L caches, and there can be multiple levels of caches, like the L1 cache, L2 cache, and depending on the processor architecture, some of the higher level caches, like the L1 caches, can be on chip, but the lower level caches, they are generally kept not on chip. They are connected through bus to the processor. So the caches have more storage capacity compared to the registers. The on-chip caches, of course, they can be accessed very fast, but not as fast as the registers, because registers, since they store very less data, that gives the additional advantage of speed. We can directly get the complete data in one memory cycle. So that is what you will come to know about memory cycles in any computer architecture course. So what happens is that we can say that in one clock tick we can get all the data that is available in the register. But if if the storage is more than that, is higher than what can be available taken in one clock tick, then of course it requires multiple clock ticks, multiple rounds of access of that device. So which is what happens in case of caches. So in order to get more data, we need multiple access of that device, so that lowers the speed at which we can also we cannot readily get the data as fast as we can get it from the registers. So the access time increases for caches, and if it is not on chip, then there is the problem of system bus that through which the data needs to travel through. So that increases the memory time. So, and after that comes the RAM, which are also, as we saw in the previous slide, they are also volatile in nature, and they are also fast, but they are not as fast as registers and caches, but they can hold more data, way more data than registers and caches. And another thing that comes into perspective is the expense part. So yes, cost per bit, as we go down the hierarchy, the devices become more and more cheap. For example, registers, they are most costly, and that is why very less storage is given for the registers. The caches, comparatively, they are less costly than the registers, but more costlier than the RAMs. So according to that, yes, the device capacity also matters, but device capacity matters up to a certain point. For example, magnetic tapes like the pen drives, they as we see generally, they store lesser data than the hard drives, but they are kept lower in the storage device hierarchy, because although they are cheaper, but we do not need that much memory, or they are very slow compared to the hard drives. So that much memory kept in a magnetic tape may not be useful at all. Even though we see hard drives, external hard drives that have almost the same access speed, but yes, that does not solve the purpose. A bigger storage means bigger spaces that is required, so that does not solve the purpose also. So there are multiple things that can be taken into consideration while when the amount of storage that is available is brought into the picture. But generally, the device storage hierarchy is created keeping two things in mind, that is the cost per bit, and if the size of the storage capacity of the devices. Sorry, not the storage capacity, the cost per bit, and the access time of the devices. So yeah, anyway, registers is the answer for this question. So let's move on to the next question. So privileged instructions are a particular set of instructions which we call privileged instructions. For example, we will study later in the course, like context switching, input output instructions. These are examples of privileged instructions. So can you tell me which mode they can run in, like user mode, kernel mode, both of them, or none of the above? Okay. 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 Anyone else, if you want to attempt the question? Okay. Okay. So yes, kernel mode is the correct answer, not both. So they cannot be run in user mode. Privileged instructions are only a particular set of instructions that only the kernel that can be run only in the kernel mode. So you must be aware that the OS can run in two modes, that is the user mode and the kernel mode, depending upon the bit. And instructions that are executed in the kernel run in kernel mode, and since since these instructions are called privileged instructions, they are very important, and these instructions have the capability to ruin something in the operating system kernel, or destroy an important part of the operating system, so that the system does not work correctly. So therefore these instructions cannot run in user mode, and they have to run only in the kernel mode. So yes, privileged instruction, that is why they are called privileged instructions. Actually they hold pretty important part. They are a pretty important part of the instructions, set of instructions that are provided. So yes, when I say set of instructions that are provided, these are actually low level instructions that interact directly with the operating system, not the high level instructions that are written in a language such as C++ or Java or something like that. So these are pretty low level instructions that interact directly with the operating system. Okay, so let's move on to the next question. Okay, so computer measurements are usually done in dash, and networking measurements are done in dash. So what fills up the two blanks? Bits and bytes, bytes and bits, bits and bits, or word and bytes? Can anyone contribute? Can anyone say what will be the correct answer? People are still joining, as I can see. Word and bytes. Okay. So computer storage measurements we have been discussing, and networking measurement we haven't gone into it that much, but okay, I'll explain it. So those of you who have not done an architecture course may not be familiar with the term word. So word, what it actually means is that when some of the addresses are fetched from the main memory or the primary memory, so not just a byte of instruction or a bit of instruction is fetched. You can only fetch a word from the storage devices. That is equivalent to saying 2 bytes or 4 bytes, depending upon the architecture. It may be 2 or 4. Generally, it is 2 bytes. So yes, when a word is fetched from the memory, only words can be fetched from the memory, but that does not mean that the storage measurements are done in words. So when we talk about computer storage capacity, what do we generally refer to? Like the configurations of a PC, what do we generally refer to? Yes, so many of you are correct, that is bytes and bits. So yes, computer storage measurements are generally done in bytes. So yes, because as we know that bytes is a collection of 8 bits, and even though word is actually a bigger term, and the OS actually does most of the transactions or most of the transfers in terms of words, but as I said, word is a term that is dependent on the OS, and it can mean 2 bytes also. Sometimes in the earlier OSs it meant 1 byte. It can mean 4 bytes also. So it is a very vague term. So Instead of that, bytes is a very concrete term, more concrete than the term words. So to the transfer, so when we refer to the computer storage measurements, we actually refer to as bytes, because those are the important. Each bit is does not hold an actual meaning, actually any meaning. So like even when you write a code, like in C or C++, when you write int or char, we refer to the storage in forms of bytes, even though it does not require 1 byte maybe, but we generally refer to the storage in terms of bytes instead of bits, because that is what is usually the standard. Like that is in terms of bytes is what the transfers happen in between the memory and the processor. But when we go to networking, the thing changes. So it is not just depending upon the processor and the memory that is available there. So it has to transfer through a wire, through a connection, through the internet. So it may be internet, it may be local, but it has to still transfer through an external wire. So in terms of that, the encoding decoding becomes a very important feature, so that all the bits are encoded properly, and at the receiver end all the bits can be decoded properly. So cryptography and other things come into picture when the networking is brought in. So when networking part is brought in, so in case of that, encoding bytes of data does not make much sense, where there you have to encode in terms of bits. Each bit is important, each bit holds information in case of networks, when you need to transfer through a larger area, when you need to transfer the data through a larger area. So that is why when we take an internet connection, it is generally in the form of bits, like 5 megabits per second, not bytes per second, or 2 megabytes per second, or 100 kilobits per second, not bytes per second, sorry. So yes, 100 kilobits per second. So that is what the networking speeds are referred to as we see nowadays. But yes, computer storage measurements, as we see every day, that RAM storage, they are generally referred to as gigabytes, like 4 GB gigabyte, 4 gigabyte, or things like that. So yeah, computer storage measurements are generally referred to in bytes, but the networking measurements are generally done in bits. So yeah, let's move on to the next question. So blank provides uniform interface between controller and kernel to manage I/O. Can anyone tell me the answer? What is the answer? That is cache, or device drivers, or registers, or none? Any of you are saying B? Okay. Okay. So anyone else? Anyone else who wants to answer? So okay, device drivers are actually the correct answer. So generally device drivers, they are provided by the vendor for an external device, for the device that it needs to perform the I/O on. For example, if we buy a new printer, so the device driver will be provided by the printer company, for example the HP or whatever printer company is there. So they will actually provide the device driver for that particular device. So what the device drivers actually contain is that they are the ones that are responsible for interacting with the OS. For example, when we connect a device, when we connect a new device with an operating system, the operating system does not know that how to communicate with that device so that we can print a page from that device, for example in case of printers. So it does not know about that, or in case of projectors it does not know how to guide that device to project the screen onto onto the lens of that projector. It does not know how to instruct how to give such instructions to the external device. So in those so to tackle those problems, so the device drivers are designed, which are actually codes that interact with the operating system, so that the operating system can send suitable messages in its own lower level language to interact with the with the external device. For example, it can instruct the printer to print a page or something like that. So at a higher level, the application softwares just can instruct a high level command, but that command has to be managed at the lower level by the operating system, and the device drivers actually help in that cause, help provide that cause. For example, the if I go back to the printer example, the MS Word software can you can just click on a printer, and then you can just click the option to print a page, but the device so the OS inside, it will interact with the device driver and instruct the printer through the instructions that the printer understands that it needs to print a particular page, and then it will take the and then it will use the storage and the bus to send the information of that page onto the printer, which will get printed. So that is why you even in the higher level application programs, you can see the available devices that are there for printing and such other drop downs. So that means that OS has identified that as a valid device which it can interact with, which which it can send instructions to. So therefore you at the higher level, the application programs also can use those devices to interact with the to provide a certain command like printing or scanning or something like that. Okay. So the caches and registers are not meant for external communication with the external devices. They are part of the storage, but they are not actually meant for communication with the external devices. They are just storage devices. That's it. And they are in fact stored on chip. They are on chip devices. So they are part of the CPU. That's it. So yeah. So direct memory. So moving on to the next question. Direct memory access transfers disk data with the help of CPU by transferring a part of the data block at a time from buffer storage to memory by generating one interrupt per data block to notify the device driver of task completion, or none of the above. Can you say which among the following is the best answer? Can anybody tell? Okay. Anyone else? Okay, I forgot to mention one thing, that is this session is being recorded. So yeah, I forgot to mention that. because I have to report this session to the NPTEL team, so I am recording this session. So yes, option C is the correct answer. So if anyone knows about direct memory access, so it will be taught in detail in the later lectures. So it transfers disk data by generating one interrupt per data block to notify the device driver of the task completion. So that is the correct answer. So what happens is that when you need to transfer some amount of data between the application program or between the application program and an external device, then you can do it in two ways. So for each bit of data, it has to go through the CPU. The CPU will provide access through an interrupt, and then it can access the external device, which is what happens in case of each keystroke. So when you press a key on the keyboard, it is an external device. So in each interrupt cycle, the CPU actually reads whatever is pressed on the key, and then it informs the operating system about that keystroke, and the operating system actually does the rest. But or even in case of mouse or something like that. But if you need to transfer larger chunks of data, larger blocks of data, for example, I need to transfer this whole video that is being recorded to an external device. In that case, transferring each bit through the CPU, which is being checked, is a very time consuming process, and the CPU is not being used very efficiently in that case. It does not need to check each data block for that purpose. So what it does is it sets up a direct connection between the devices that needs to transfer the data. The OS sets up a direct connection between those between the devices, and there is an external controller, called the DMA controller, the direct memory access controller, that actually looks over this whole transfer of data. And when the transfer is completely done, then the direct memory, the DMA controller informs the OS that the transfer is completed, and then the OS takes care of the rest. But yes, actually there are two subparts of direct memory access. One is the burst mode and one is the cycle stealing mode, which will be taught in detail in the later lectures of the course. But what happens is that in burst mode, the process continues in the way that I just described. That is, it takes a certain chunk of memory, and after the whole data transfer is done, then the DMA controller informs the OS that about the completion of the task. But in cycle stealing mode, the OS regularly checks back to see if the transfer is done, if the transfer is complete. So these are just two types of direct memory access. So yes, anyway, it is faster than the interrupted mode, where an interrupt is generated for each byte of transfer, or for each word, for each byte of transfer between the device and between the external devices. So yes, it is faster. So that is why direct memory access comes handy in some cases. But of course, in certain other cases, you cannot set up a DMA transfer. For example, in case of keystrokes, you cannot set up a DMA transfer for that. So it needs processing. Each key hit may need processing. So for that, yeah, direct memory access will not work. So moving on to the next question. This is probably the last question of this session. So can you please point out the incorrect statements among the following? That is, on-chip communication is faster in multi-core systems than multiple chips with a single core. Multi-core system is more efficient than multiple chips with a single core. Or multi-core systems are multi-processor systems, and all multi-processor systems are multi-core systems. So which among the following do you think is incorrect? So someone is asking, is there any WhatsApp group for this, I think for the course. So if you have any doubts, you can post it in the discussion forum. So yeah, you have to keep in mind which one is incorrect. You have to point out the incorrect statement. Okay, let's go to the answer. So yes, D is incorrect. That is, what happens in multi-core systems is that there are multiple processing cores, but some of the other resources may not be present as a multiple, like there are registers, there is a program counter. So there may not be multiple copies of all the resources that are required. So if you go to the von Neumann architecture, there's just not the processing units. There are other devices also that needs to be there along with the processing units in a CPU. So those are not present. Those are the copies. So those are not copied in multi-core systems. So thus the main intention, main idea is that to provide multiple processing, but with a cheaper system, but with a cheaper cost, overall cost, CPU cost. So that is why there are multiple processing cores which can process the data, which can process the data multiply, but all the devices are not copied. So does not have multiple copies of all the devices like registers and program counter and so on and so forth. So the first point is on-chip communication is faster in multi-core systems than multiple chips with a single core. So in this of course is true. That is, once it is on-chip communication, as I discussed previously also. So on-chip communication is fastest since it is very near to the processor. So it is very fast. But multiple chips, it may need to access a single bus. So once the bus comes into picture, the access time and the access is also a major factor that contributes to the delay. So if there is a single bus, for example, and multiple chips are transferring data through that single bus, then it needs to wait for its access to transfer data through that bus, which delays the process. Moreover, the data will also come in a streamlined mode and not in a parallel mode, which may be a problem, which may contribute to the slowness of the multiple chips that may not be present on in closer to the CPU. So coming to the second point, multi-core systems, of course they are more efficient than multiple chips with a single core. So the core is the core is like the processor of the system. So multiple chips with a single core does not speeden up the process. If you do not have the brain, if you do not have multiple processors, then even if you can store more data, that does not provide you with good advantage compared to where you can have multiple cores, multiple cores or multiple processors which can process data multiply. So it provides more efficiency. Even if you do not have multiple chips in a multi-core system, it can control the data in a specific way. It can use the data so that it does not have to wait for more data, and the chip chip space is not a limitation. So it can manage the data in a certain way. So it is more efficient, of course, compared to multiple chips with a single core. And yes, coming to the third statement, all multi-core systems are actually multiprocessor systems, as you may know. So yes, for multiple So for multiple processors, there needs to be yes. For saying that we have for saying that we have a multi-processor system, all the on-chip devices needs to have a copy, not just the cores of the system. So yeah, so the multi-core systems are multi-processor systems, but not the vice versa. So yeah, this that takes me to the end of this session. So these are actually, I have included some questions from the current lectures, and most of the questions from the previous year NPTEL course on operating system. So hopefully this will help you solving this week's assignment. So yeah, sessions like these will be held every Tuesday from 6 to 7. There are 2 other sessions, NPTEL live sessions for this course that will be held on Friday, I think. I'm not sure about the timing, but this session will be held on Tuesday 6 to 7, where we'll be solving some questions, some problem questions with regards to that week's course lectures. So this was mostly a theoretical lecture, a theoretical problem discussion session, not a lecture, a theoretical problem discussion session. So in the future weeks, it will not always be like this. Okay. Sir, I have a question. Please show the question. Please present. Okay, I'll present from questions 1 to 8. Okay, sure. I'm not sure whether the questions will be available to you or not, but I will try to ask Professor if the questions will be communicated to the students, if the presentations will be communicated to the students. Anyway, what I was saying is that the future sessions will be more of a problem solving session, where we'll go more into the in-depth of the operating system. This was kind of a mixture between operating system and computer architecture kind of thing, where the questions were mostly theoretical. We will, in the future courses, we will go in more depth towards the problem solving sessions. So yeah, anyway, thank you for your time. So these are the questions that you were asking. I'll just glance through the questions. Yes, of course, there will be numericals coming in the coming sessions, depending upon which what is being taught in in that week's theory course. So I will of course include problems. Majorly, I will try to include problems only. It will be a major problem solving session, not a theoretical session as this one is. As I said, this is mostly an introductory session, and I did not find any problems from the introductory session. So yes, I had to spend my time mostly on theory. Sorry for that. So yeah, from the next session, I will try to make it more interactive with more problems. So yes, thank you all for participating also. I was constantly seeing some answers on the chat box. So thank you all for participating. Hopefully the hopefully the future sessions will be more interactive. And yeah, this is the 5th question. This is the 6th question. And the 8th question. So yes, if you missed any question, just you can tell that in the chat box. Just provide a header like Tuesday discussion, Tuesday NPTEL live discussion or something like that, so that I can keep track. Otherwise it may get lost among other questions in the discussion forum.
Hello.
Yeah.
Excuse me, sir.
Yeah.
Sir, thank you, sir, for presenting the question 1 to 8, because I have a bad network issue. That's why I asked you to present from
Okay.
question 1 to 8.
Okay.
Sir, I
No
have a
problem.
question that we have daily on Tuesday classes as from now.
Yeah. No, these are like discussion forums where we'll be discussing problems. This is not a lecture session or anything like that. We'll be discussing problems related to that week's lectures that are available in the NPTEL website. So based on that lecture, I will be framing a few problems, and we will be solving those here inside this 1 hour session. Okay.
Okay, sir, sure.
Yeah.
Thank you, sir.
Yeah. So anybody is free to join this session, provided that you signed up for the course, of course. So yeah, I will stop presenting now. Thank you all for your time. So yeah.